Good afternoon, everyone. Let's get started. Today, we are going to talk about binary search trees. First, course logistics. Homework 7 is due on May 16th. We first want to talk about the motivation of why we are studying binary search trees, and then discuss what binary search trees are. In the last lectures, we stated that we would like to build efficient sets and dictionaries because we could solve numerous problems with dictionaries. And if you really develop some practical applications or your own programs, then you are going to use dictionaries quite a lot. So that's why we are interested in building efficient sets and dictionaries. And we set a goal to make these operations O log n. So in the last class, we discussed how we can make find, insert, delete, find min, and find max operations O log n. And we use tree-like data structures. By the way, what is a binary search tree? A binary search tree is a special type of binary tree, and the value in each node must be greater than or equal to any value stored in its left subtree. And the value in each node must be less than or equal to any value stored in its right subtree. So what do these two statements mean? I'll show you a picture. So when you see this one example of binary search tree, let's have a look at this node. This node has the value 5, and this value is greater than any values stored in its left side. So 1, 2, 3, 4 are smaller than 5. On the other hand, this value is smaller than any values on its right side. So 6 and 7 are greater than 5. And these two properties are satisfied for all the nodes. So when you have a look at this node, 2 is larger than 1, which is on its left side. However, 2 is smaller than 3 and 4, which are on its right side. So these two properties should be satisfied for all nodes. So this is what a binary search tree looks like. And there are some features of binary search trees. Like a normal binary tree, we can traverse a BST. BST is an abbreviation of binary search trees. And you can do pre-order, in-order, or post-order traversals. However, it is noteworthy, you need to keep this in mind, that in-order traversal in BST will be in ascending order. So if you have a look at this binary tree, when we perform in-order traversal, that is going to be, we're going to wrap this tree in this way. And when we are passing the bottom side of this node, we're going to write down the value of that node. So when we travel this node in order manner, then we do not write down 5 because we are passing the left side. However, when we reach here, we reach the bottom side of 1. So we're going to write down 1, 2. We're passing the left side, so we just pass. And 3, 4, 5, 6, 7. So the in-order traversal results in a ascending order sorted of the values in the nodes. Okay. Therefore, the in-order traversal is the most frequently used traversal method of a BST. Okay, that was the concept of binary search trees. From now on, we are going to implement binary search trees. But before we go on, do you have any questions? Cool. Let's move on. So we are going to implement binary search trees. And after that, we are going to implement a dictionary using binary search trees. So first of all, we're going to implement a binary search tree. Because we need to implement a special type of binary trees, we need to define a node. In the last class, because we dealt with complete binary trees, we just use arrays to implement complete binary trees. However, in binary search trees, as you can see from this figure, this binary search tree cannot sometimes are not incomplete. So we cannot use arrays to implement this structure, but we are going to use linked list style binary trees. So that's why we are implementing a class node. So we're going to use linked list style implementation. Okay, first of all, we need to define the constructor. And because we are going to use this binary search tree for implementing dictionaries, we're going to receive two values. The first thing is key, and the next thing is value. And because this class node, is going to be a binary tree, we need to receive two things, the left subtree and right subtree. So this is how we are going to define the constructor. And we just need to store the past arguments in this way. So this is pretty simple. And the next thing we're going to implement is find method. So when we are given a key, we want to return the node that has the key, the given key. And I'm going to show you an example here. Let's say we have a tree that looks like this. It's some time for me to write down this trees. Sorry for that. Let's say we have a tree that looks like this. And when we want to find, let's say 4 in this binary search tree, then what we are going to do is we first start from the root and the target is 4, let's say. Then if this value is larger than the target value 4, we need to search for the left side. So from here, we go to the left part. And if we compare this value 3 with the target value, target key 4, this one is smaller than the target value 4. So in that case, we're going to go to the right side. Because the nodes are sorted, the search becomes very useful, very efficient, and we're going to implement that. So if the key we want to find matches the key at the current node, then we are going to just return self. However, if key is smaller than the current key, then we are going to go to the left side. And we can just call the find method on the left side like this. However, this is only when we have left part. Otherwise, we are going to just return none because we don't have a key that is matched. Okay. And else, we are going to return self right, find the key. Of course, we need to have the right side. Else, we are going to return none. So because we have the binary search tree properties, the find method becomes very easy to implement like this. Okay. And another method that we are going to implement is find first. This one corresponds to find smallest. So we want to find the smallest key in this binary search tree. So this is one method that is going to be very useful in the towards the end of this course, this lecture. And a similar method that looks like find first is find last. Using this method, we want to find the largest key in this binary search tree. So this is today's first PPP exercise. Take some time and try to implement these two methods. And as usual, please send me a PPP message before you tackle these two methods. I'll give you one more minute. All right, thank you for sharing your answers. In fact, there are two ways to solve this problem. Okay, this one is from Hyunsuk. First, the first approach is using iteration. So this one is from Hyunsuk. So to find the smallest value in this binary search tree, we just need to go to the leftmost part. So from here, we go to left. From here, we go to left until we reach the none. Okay. So we first start from current, and current is going to be self. And while we have left part, we just move to the left part. And then we just return current. So this is our first approach using iteration. And find last is going to be very similar. So we just go to the rightmost part, and that is going to be the largest value in this binary search tree. So rather than going to left, we're going to go to the right part like this. So this is the first approach using iteration. And second approach is using recursion. One way is we are going to call the left part and find first again if we have left part. Otherwise, we are going to just return self. So this is the second approach using recursion. So using recursion, we can solve the same problem. And for find last, we can do similar thing. However, here, rather than going to the left part, we're going to the right part, and rather than finding the first, we're going to find the last, like this. Okay, so this is how we find the smallest and largest key in a binary search tree. And the next thing we want to do is insert operation. So we're given key and value. And to implement this method, we need to think about two cases. The first case is there is already a node with the given key. In this case, what we are going to do is find a node with the given key and just update the existing node. That's what we are going to do. And the second case is, as you can expect, there is no node with the given key. If this is the case, what we are going to do is find the right place and create a new node. So this is what we are going to do. So this is our today's second PPP exercise. Take some time and try to solve this problem. And as usual, please send me a PPP message All right, thank you for sharing your answers. Let's solve this problem together. We're going to implement this method using recursion. So we first need to define the base case, and that is going to be our first case. And that means if the given key matches the self key, then what we just need to do is update the new value. Okay, so that is the first case and our base case. And the second case is we need to find the right place to find this key. So if this key is smaller than the key stored in the current node, and then we need to have a look at the left part. We need to inspect the left part. And if the left part is none, that means we just need to create a new node with this key and value. And if left part is not none, then what we are going to do is call this insert method again for the left part. That's what we are going to do. So be careful. If this key is the same as the current key, then we just need to update the value of the current node. However, if this key is smaller than the current key of the current node, then we just need to inspect the left part. And if the left part is none, that means we reached the end. So we are going to just create a new node using this expression. Otherwise, we keep searching for the right place on the left part. So the last case is when key is larger than self's key. In this case, we are going to do a similar thing. We just need to check whether the right part is none or not. If it is none, we're going to create a new node with the given key and value like this. Otherwise, we're going to keep looking for the right place using the insert method like this. Do you have any questions regarding this method? Cool, let's move on. So up to this point, we defined binary search tree, and we had a look at how we can find a node in the given binary search tree. And using this, we developed this find method and implemented how we can find the smallest key or the largest key in the binary search tree. And we had a look at how we can insert a new key or update the key already inside the binary search tree using this insert method. And the next step we are going to take is implementing the remove method. So we had a look at how we can update a node or create a new node. And the next step is how we can delete an existing node. Deleting an existing node is quite tricky. So I'm going to explain how we can implement this remove method first. And then I'm going to show you how we can implement the concept. And we need to think about two cases. The first case is, of course, we just assume that this binary search tree has the key past this one. Okay, we are not going to check the error case here. So when we want to remove a key from this binary search tree, there is going to be two cases. The first case is the node of interest has 1 or 0 child. So let's say we want to remove 11. And this one has 0 child. And if that is the case, what we need to do is just remove the node. Or possibly we need to create a new connection or substitution. Substitution. So what I mean by this is, let's say we want to remove 11. And because this one has 0 child, we just need to remove this one. And that's all. However, if we want to remove 9, and this one has just 1 child, then what we can do is just remove this one and substitute this one with its child. So 7 will go here. Okay? So if the node we want to delete or remove has just 1 or 0 child, the things are very simple. Just remove that one and replace that one with its child. That's all we need to do. And the second case is somewhat tricky. The node of interest we want to remove has 2 children. In this case, things are somewhat complicated because we need to maintain the BST property. So what was BST property? The value in its node, in each node, must be greater than any value stored in its left subtree, and the value in each node must be less than any values stored in its right subtree. So these 2 properties are BST properties. And when we remove, let's say 5, then this one has 2 children. And after removing this 5, we still need to maintain the binary search tree properties. So how can you do that? This one takes 2 steps. The first step is, of course, we need to remove the node. So what we are going to do is just remove this one. Okay? That's what we are going to do. And the second step, when we remove a node with 2 children, is exchange the deleted node with the smallest value in the right subtree. Okay, so what does it mean? The smallest value in the right subtree. So this one, originally 5, has a right subtree here, 9, 7, and 11. And what we are going to do is remove this one first and go to the right part and find the smallest value in its right subtree. So we are going to find the smallest value here, and that is going to be 7. Because when we want to find the smallest value, we just go to the end of the left part, and that is going to be 7. And we are going to remove this one like this and place 7 here. Then the BST properties are maintained. Why is it so? Because this value is the smallest value in the right subtree. However, because it was in the right part, it is larger than any values on the left part. So if we place that value to the root, then the binary search tree properties are going to be maintained. So that's why we are trying to find the smallest value in the right subtree and place that value at the root position as a new root. So this concept might be somewhat complicated or confusing at a first glance. However, this one is very simple when you once understand it. Any questions regarding this concept before we start implementing this method? All right, let's move on. So what we are going to do is check whether this given key is smaller than the key stored. And we need to check whether the left part is not none. Otherwise, we cannot repeating the searching process. And if we have the left part, then we're going to replace the left part with the remove key. And the thing is, this remove method is going to return the new node, new root. So why is it so? So let's say we want to remove 9. Then I told you that we need to replace this 9 with its only child, 11. So if this method returns 11 when we are trying to remove 9, then we can just place this 11 to this value. So that's why we are returning the new root. Once I finish implementing this method, this concept will be clearer. So if you have the left part, then we go to the left part and call this remove method. And else if key is larger than self key and self right is not none, we do the same thing. Self right is going to be self right dot remove. And this is the case where key, the given key matches the key stored in the node. And we need to think about 2 cases. We need to think about the second case first. We have 2 children. What we are going to do is first check whether we have the left part or not. And self right is not none. So because left part is not none and the right part is not none, that means this node has 2 children. So this is the second case we discussed. Then we need to remove self, okay? And I told you that we need to find the smallest value in the right subtree. And what we are going to do is self right. We call this find first method on the right part, like this. And this one will return the smallest value in the right subtree. And we are going to replace the key with this one. So we found this node, which was 7 here. And we're replacing this value, the root value, with the 7 node. So this is what we are doing here. And we need to update the right part. And how are we going to do that? We're going to call a method called remove first here. Okay, and this will update this part. So this one, 7 goes here, and then so 7 still remains here. And we're going to delete this node. Then remove 5 is complete. All right. So this was our second case. And we need to think about the first case as well. That is, we're going to just return self left if self left is not none. Else, we are going to return self right. So we don't have this one because. So if we have left part, then we are going to just return the left one. Otherwise, we're going to return self right. And because when we remove this part, if you have the right child, then this one will return this node. And automatically, this will go to this position when we try to remove the node with the value 9. Okay? And lastly, we're going to return self. So this is how we can implement the remove method. And one more thing we need to do is implementing remove first. Okay? By the way, do you have any questions regarding this remove method? This one might look somewhat confusing at a first glance, as I told you. But you could think about it over and over, and I am pretty sure that you could understand this. Okay, and the next method we need to implement is remove first. This one, remove the node with the smallest key in the subtree rooted at this node, at the given node. And this one returns the new root as well. So this one is our PPP exercise. Try to implement this method. And as usual, please send me a PPP message before you start implementing this method. I'll give you 1 more minute. All right, let's solve this problem together. This one is from Hyunseo. We first need to check whether we have the left part or not. If we have left part, that means, right, so let's think about these two cases. If we have left part, that means this node is not the smallest one. However, if we do not have left part, left subtree, that means current node is the smallest node. So if that is the case, we are going to return the right subtree. So in this figure, if you do not have the left part, and if you just return the right subtree, then this node will be replaced with 11. So that is the case. And if we have the left part, that means we need to go to the left part. And we're going to update the left subtree by calling this remove first method on the left part. And then we're going to return self. So this is how we can implement this method. Okay. So this is the complete implementation of binary search tree. We initialize the binary search tree and we implemented the find method. And after developing this find method, we implemented find the smallest key in the subtree in the binary search tree and find the largest value in the given binary search tree. And we had to look at how we insert, create a new node or update, and how we remove a node in this binary search tree. So this was the complete implementation of binary search tree. And from now on, as I told you in the beginning of this class, we're going to implement a dictionary using binary search tree. So once we have binary search tree, implementing dictionary becomes very simple. We are going to first implement the constructor like this. And the root at first is none. And we're going to implement a find method. With the given key, we want to check whether we have the key inside our binary search tree or not. And because we are going to store a binary search tree in this root, we are going to call find key method here if we have self root. Otherwise, we are going to return none. Okay. And get item method becomes very simple. We just need to find the key like this. And if n is none, that means we do not have this key inside our binary search tree. In this case, we could erase a key error that we do not have this key inside this dictionary. Otherwise, we are going to return the value of that node. And we can also implement this contains method, whether this binary search tree contains a node with a given key. And what we are going to do is we just call this find method and check whether this one is not null. Okay. And sometimes we want to find the first key, that is the smallest key inside the dictionary. Then what we need to do is let's call the find first method. If we have self root, else we are going to return none. And last key is simple as first key. We're going to call a find last if we have self root, otherwise we're going to return none. And we can also implement this del item method, which will delete the key. If we have self.root, then we're going to update the root by removing the given key. So up to this point, we talked about how we can find some keys inside a dictionary or check whether this dictionary has a given key or not. And one of the most important things is how we can insert new items to this dictionary. That is, we're going to accomplish that goal through this set item method. We first need to check whether this root was initialized or not. If this one was not initialized, then we're going to initialize this one with a new node with the key and value. Otherwise, we're going to call this insert method to this root. So this is the implementation of a dictionary using binary search tree. So as you can see here, this is a wrapper class for binary search tree. Basically, we are using binary search tree as a dictionary. However, to improve the usability, we're just implementing a new class, dict. So that's all. And basically, we can just extend this binary search tree, this node class, to implement dictionary. However, we just want to separate the core part and the usage part, and that's why we are implementing this class dict separately. Okay. And so let's test our implementation a little bit. So we can create dictionary like this. And to this dictionary, because we implemented the set item method, we can insert these new items like this. And the key is going to be 7. This one will have keys 3. And G is 1401 like this. And we can print like this. And this print method prints the level. So 7 is at the zeroth level, and 3 is at the first level. So it is actually tree, binary tree, that looks like this. Okay. So this one visualizes this representation. And we can also update spring. The node with the given key 7 like this. So now D7 contains EC2202 spring. But before that, it stored this one. We can do this kind of things. And you can also test other functionalities on your own after class. And before I finish this class, I want to show you one problem of our implementation. Let's say we want to insert 100 numbers. Like this. So what we are doing is we are inserting numbers to this dictionary from 1 to 100. Actually 99. And let's see what happens. If we do this, as you can see here, 1 is at level 0, 2 is at level 1, 3 is at level 2. So basically this binary search tree looks like 1 connected to 2, connected to 3. So basically this one looks like linked list. And we call this unbalanced binary search tree. And if this happens, all the other operations that we implemented, like find method or insert method, all the other methods, takes O n. However, if you have balanced binary search tree, then the time complexity is going to be log n. So this one does not change anything, even though we insert new items. It just finds the right place for the new node and insert it in the found position. Sorry for that. So this one becomes unbalanced once we insert items in order. So it becomes a problem. So we cannot make this operation very efficient. And in the next class, we are going to make our binary search tree balanced in all cases. Okay? So this is the end of today's lecture. If you have any questions, you can stay here. Otherwise, you can leave now. Thank you for your participation.